All right, so as I was saying, we discovered the Van Allen belts, which are charged particles that get trapped in the Earth's, it's certainly way outside of the atmosphere, but they get trapped, and the charged particles bounce back and forth within the Earth's magnetic field. Here are some pictures of aurora. All right, the next subject is the tides. The tides are caused by the moon, by the position of the moon, and also by the changing angle of the moon and the changing angle of the sun. It turns out. We'll start with the moon first of all. The bulge that's on this side, on the side that is facing the moon, in the direction of the moon, is pretty easy to understand. It's really just gravity. The moon is so close to the Earth that it pulls harder on the water on the side that is facing the side of the Earth that's facing the moon than the other parts of the other parts of the ocean. So this is called differential gravitation. All right. So there's a greater gravitational pull just due to the closeness of the Earth. All right. Now the tide on the other side, the high tide on the other side is more difficult to explain. Really, what it has to do with is inertia. So basically, what happens is, just looking down on the Earth, this is you get this tide, of course, which is caused by, as I said, differential gravitation. The tide that is roughly 12 hours later, the high tide that is 12 hours later on the opposite side of the Earth. Why is the ocean? Why is all the water bulging in this direction? That at first it doesn't really make sense, and so the reason has to do with this. It's the same idea as if you had a bucket of water and you tied that bucket of water to a rope, and if you spun the rope fast enough, the water would stay in the bucket. You're swinging it straight up and up in a giant circle. All right, so that's inertia. So the water has to have a place to pile up, and it does it in the opposite direction of the tidal bulge that's caused by differential gravitation. So that's where this bulge comes from. So the low tides, are at 90 degrees from the high tides. And now the thing about that is, of course, the moon is moving. Each day, the moon moves by about a little less than an hour. It moves about 50 minutes from where it was. So, for example, if you go out, let's say you go to Myrtle Beach and it's high tide exactly at 9 o'clock, and you go out the next day, and you want let's say you want high tide to occur, or you were measuring high tide, that it wouldn't occur until 9:50 because the moon has moved a little bit, right, in its orbit around the Earth. All right. So let's go into these the high tides and low tides. All right. So basically, if you take some point on the Earth, let's say down here, with where we are in South Carolina. Basically, what happens is the Earth rotates into the low tide, and then 6 hours later it rotates into the high tide, and so we experience that along the coast, and then 6 hours later it's in the low tide again, and then 6 hours later it's again in the high tide, and so it keeps repeating. The thing is, the high tide has now moved the next day by, as I said, 50 minutes. 50 minutes further along, like I said, if it was 9 o'clock one day, and then it would be 9:50 the next day, and then 50 minutes later the next day, and so the tides are moving. All right, so now the moon is the main cause of the tides, but there's other tides called spring tides and neap tides. So the sun has an effect on the Earth's tides, just like the moon does, but of course the sun is much, much further away than the moon. In terms of miles, right, the moon is 250,000 miles away, whereas the sun is roughly 92 million miles away. And so the moon has much greater effect on the tides than the sun does, but because the sun is so massive, it has almost half as much an effect. And so it turns out if the moon and the sun and the Earth are lined up, then you have higher than normal high tides and lower than normal low tides. And those are called spring tides. Not because they occur all the time. They were probably first noticed in the spring, and that's why they're called that. All right, so when and of course this happens during a new moon or a full moon. That's the only times that the Earth, moon, and the sun are lined up in a straight line. If the Earth and the sun and the moon are at a right angle or 90 degrees from each other, then what's happening is the gravitational influence of the sun is decreasing the effect of the tides, caused by the moon, and so that it's basically countering what's going on with the moon, and so these are called neap tides. So it would be the lowest high tide that's going to occur, and they can only occur when the moon, the Earth, and the sun are at 90 degrees from each other, and that of course occurs during the phase of first quarter and the phase of last quarter. All right, and the moon is actually causing a force, a drag force on the Earth's rotation. That the tides are actually what's doing that, and so the Earth is actually slowing down over time. It's slowing down very, very slowly. It's not something you'd notice even in your entire lifetime. It slows down by about 0.002 seconds once every 100 years. That's how that's how slow the Earth is slowing down. But it is slowing its rotation down, and in the past it was rotating much faster than it is today. All right. The other thing is that the Earth, the moon rotates in what's called a synchronous fashion. One side of the moon always faces the Earth, and the Earth, the moon does spin about its own axis, but it does it. Let's see, kind of like if you ever played the game Ring Around the Rosie as a child, as you go around, you spin, but the same side of the moon will always face the Earth, but it spins once. So it takes one rotation to spin about its axis once. So that's the way that's what's called synchronous rotation. And the moon isn't the only. Our moon is not the only object in the solar system that does that. There are several moons of Jupiter and Saturn that do this. All right. In fact, when we start talking about Mercury does a similar thing around the sun, although it's a little bit more complicated. All right. So this is just the summary of everything we talked about in this chapter 7. All right. So I'm going to stop it there.